What if I told you that the speed of light, this constant of the universe, was actually nestled into the very equations of physics themselves? And so that's the theme of today's video. Today we're going to be diving into Maxwell's equations, which are these four equations written here, and they're basically just this set of elegant laws that not only describe electricity and magnetism, but also predict that light itself is an electromagnetic wave. And so we're going to use these equations and figure out how physicists manage to extract the speed of light from it. So the first way we want to, start with these equations is let's give ourselves a reason to apply it. So let's go ahead and create a diagram. So I'm just gonna start by making life simple, a rough XYZ sketch. So here we've got our x-axis or the I-hat direction, and then we've got my y-axis or my j-hat direction, and then my z-axis or my k-hat direction. And so say you have some electromagnetic transverse wave that is propagating through space in this I direction, right? And that's its velocity, v. And that's in the I hat direction. And so as it propagates through space, this electromagnetic wave will have an electric field that we will call E, and it will also have an associated magnetic field that is also perpendicular to the other two and will be the magnetic field, so B. And so the electric field will just act in the J direction, and this magnetic field will only act in the K direction. So from this we can express that pretty much our velocity is going to be, our velocity is just going to be v equals um, v I hat plus 0 j hat plus 0 k hat. And then our total electric field E will just be 0 I hat, and then magnetic field will be 0 I hat plus E as a function of position and time, j hat plus 0 k hat, and then this one will just be 0 j hat plus b of x t in the k direction. Okay, cool. We've done that, and notice that already we see that this total magnetic field and this total electric field are already showing up in Maxwell's equations. And the only now confusing bit is, what is this nabla? Well, that's just an operator, and it's just pretty much the gradient. So we can just define nabla to be this row vector of partial derivatives. So that's your partial x, partial y, and partial z. And that's a row vector. So now all the equation is asking us to do is you take the cross product of the two quantities, and then we can say that that is equal to this partial b by partial t. So let's go ahead and start with this first one here, which is nabla cross E, or the curl. So nabla cross E is just pretty much the cross product of this and this nabla operator here and this electric field here. So let's go ahead and do that. So we can express this as the determinant of a 3 by 3 matrix with I, J, K, and then nabla, which is partial X, partial Y, and partial Z. And then for our electric field, we have 0, E, and 0 once again. And then I'm just probably I should do this in a different color. I think blue is fine. And then if we go ahead and compute this determinant, so we can just do our usual cofactor expansion. I'm going to block out this column and this row. Um, yeah, there we go. And then I take the determinant of this. This is 0, the determinant of this, and this one will just become nabla cross E. And I direction will become partial E by partial Z, E of xt, in the I direction, so I hat. And then block out, now we're going to block out this column here, and it's going to be a minus. And then we take this and this product, and both of them actually end up being 0. So this is just going to become 0 j hat. And for the k direction, we block out this, and then we're going to get a plus, and then partial e of xt by partial x, and then this one is just going to become a 0, the product of this, and this is in the k hat direction. So let's tidy this up a little bit. Now, E only depends on x and t, so simply taking the z derivative is going to yield a result of 0. So the final curl, nabla cross E, is just equal to 0 I hat minus, I'm just going to plus 0 j hat plus partial E of x t partial x k hat. Go ahead and box that. Now, next what we can do is, if we go back up here, we see that all of this is equal, this nabla cross E here is equal to minus partial B by partial T. So we can actually go ahead and reduce this a bit more, I think. So now let's write that this follows on that partial E of x t by partial x is equal to minus partial b by partial t. And we can call this now our very first equation. And let's call this equation 1. Cool. Nice. I'm only calling it that equation because I don't really know what else we can do further after this. So let's come back and now let's do nabla cross B. So I'm going to do nabla cross B in a different color. I'm going to try green. Um, this line here. And then, so for nabla cross B, right? So nabla cross B, the curl, is just going to be, once again, this determinant of another 3 by 3 matrix with I, J, K, and then partial X, partial Y, partial Z, and then, and from this diagram, B is only in the K direction, so this will just be 0, 0, and B. And once again, just like we did before, doing the cofactor expansion of this, I'm going to block out this entire row, block out the first column, take this determinant, we're going to get partial B of xt, partial y, and then the other one becomes 0, so I hat. And then next, for the j direction, we're going to block out the j column, and then take this, and it will become a minus, so minus partial b of x t by partial x, and then that's a positive, and then this will just become minus 0, so j hat, and then for the k direction, block out that entire column, and the both products will end up becoming 0, so we're just going to write plus 0 k hat. So we can express that nabla cross B is equal to this term here is just going to go to 0 since b does not depend on y. So that's just going to become 0 I hat, and then minus partial b of xt, partial x, and j hat plus 0 k hat. And then from this point, we can just equate this and mu naught epsilon naught partial e by partial t as from Maxwell's equation. So what we can now write is that it follows from here that minus partial b of xt partial x is equal to mu naught epsilon naught partial e by partial t. And then I'm just going to take this minus to the other side, so we're just going to get partial b of xt is equal to, partial x is equal to minus mu naught epsilon naught partial e by partial t. And I think at this point we can go ahead and box this and call this equation 2. Okay, so now what's the whole point of doing all this? We're trying to solve for the velocity of some electromagnetic wave that is propagating through space. Now, luckily for us, there is an equation, right? So there's this general wave equation, right? So general wave equation. And the equation is as follows. So it is second order in space derivatives is equal to 1 over v squared times the second order in time derivative. This is the general wave equation, and what's useful is it contains this. It contains velocity, and that's kind of what we're trying to solve for, right? So if and only if we could somehow link equation 1 and equation 2 and bring it in the form of this general wave equation, then we could maybe solve for this velocity of the wave equation that is propagating through space. So let's try to do that. So the first thing I kind of want to do is I'm inclined to go back to equation 1, and if I want to turn it into second order of space derivatives, then I'm going to do this in another color now. I'm going to make this orange. Then I could just take the second derivative of this with respect to x. So what's that going to look like? So if I just go ahead and put a partial x and then it's equal to x derivative. Now look at this. All I've done is I've just taken the second x derivative, the derivative with respect to x, and now let's actually carry out some and see how it goes. So partial squared e of xt, that looks like a 2, is then just going to be equal to all of this. But what we can actually do is we can swap these two derivatives, and I can just go the time derivative of partial b by partial x. And now the reason why I did that is because if you realize this is actually an equation for partial b by partial x. So at this point, I can just make a substitution, right? I can just go ahead and now copy out this side. And second order in space is then just going to be the negative partial time derivative, and partial b by partial x is minus mu naught epsilon naught partial e by partial t. It looks like things are working out quite nicely here because in doing this is going to become second order in time derivatives, and we already have an equation that is second order in space derivatives. So let's not get too ahead of ourselves and just do the math and see where it takes us. and then these negatives will just cancel out, and so we're going to get mu naught epsilon naught, and then the second derivative, partial derivative of E, and we get this. We get this equation here. And I'm actually going to box that in a different color. I'll box it in red. And we get this equation here. And look at this. This is second order in spatial derivatives and second order in time derivatives. And I'm just going to try to copy the general wave equation right underneath this. So partial squared y, let's call y a function of position in time, and 1 over v squared, and then, oops, that looks pretty bad. And we can sort of start equating things. Now, on the left-hand side, we have a component that is second order in space derivatives and second order in time derivatives. So these two match. The only things that do not match is just these coefficients. So this wave, this electromagnetic wave that is propagating through space can only match the wave equation if and only if this following condition that I'm about to write here, that 1 over v squared equals mu naught epsilon naught. If and only if these two are equal, then then it is an electromagnetic wave. Right? So solving for v, we get v equals 1 over the square root of mu naught epsilon naught. That is the velocity that this wave is propagating through in space. And we know that mu naught is the permeability of free space with a value of 4 pi times 10 to the minus 7 Henry per meter, and then epsilon naught is the permittivity of free space, which is 8.85 times 10 to the minus 12 farads per meter. And if we go ahead and punch these into the equation, then you get that V is somewhat about 299,792,458 meters per second, or the more acclaimed 3 times 10 to the power of 8 meters per second, which we all know today as the speed of light. And so that is how we can use Maxwell's equations to pretty much uncover the speed of light. And yeah, so that's that. And thanks for watching.